Lawrence Bragg, who just over 100 years ago worked with his father to develop a completely new scientific discipline, which we call X-ray crystallography. And this is the subject which enables us to study the atomic arrangements in crystalline materials, which is the bulk of solid materials. This is the reason that we know about the structures of metals and alloys, pharmaceuticals, drugs of various kinds, inorganic, organic compounds, proteins, viruses, and of course DNA. Their work back in 1912, 1913 started a complete revolution in science, and they obtained together the Nobel Prize in 1915, with William Lawrence Bragg being the youngest scientific Nobel Prize winner ever at the age of 25. Lawrence Bragg made his discovery when he was only 22 years old in 1912, to working on some experimental results done in Germany, but they failed in Germany to solve what they were seeing properly, and it was Lawrence Bragg who had the vision to realize that there was a simple way of explaining the effects that the Germans had. And behind me, there's two paintings here. Both father and son were quite competent artists, and I think that it's that combination of being a scientist and being an artist that enabled them to work through the formalism the German scientists had and come up with a very simple solution to what they were doing. And that's what kicked off X-ray crystallography. So this is a very important advance. The first crystal structure done in 1913 is illustrated here. This is Bragg's original model of sodium chloride, common salt, with an alternating arrangement of sodium and chlorine atoms. It goes on and on infinitely. If you make it big enough, you get a crystal of salt. It was highly controversial at its time. Lawrence Bragg published that in 1913, and he and his father published the structure over there of diamond, which is the same structure as silicon, one of the most important solids of the 20th century. So the two of them really established something very important. They obtained the Nobel Prize in 1915. We have one of the Nobel Prize certificates here, so that you can see rather beautiful lettering and so on. Now, one of the things that... oh, by the way, I've given you, most of you at any rate, a pamphlet. I haven't got enough for everybody, but this is to do with an exhibition that we mounted a few years ago at Warwick University, entitled The Two Braggs. We had a lot of their equipment, and if you look on the pamphlet, you'll see there's a kind of potted history of the Braggs. William Bragg, the father, was here until 1942. He died while in office, and his son, Lawrence Bragg, came in 1954 and was here into the 1960s. And you could say, really, in the 20th century, the Braggs were the Royal Institution. That's how important they were. Okay, so one of the things that Lawrence Bragg did when he came here was he instituted a series of lectures for school children. Something like 100 to 200,000 school children went through this lecture theatre, watching Lawrence Bragg demonstrate science to them. And you can see on the right here, there's a picture of about 60 years ago of Lawrence Bragg really enjoying himself talking to the young people, doing experiments. And I put this one up here because you can also see on the left-hand side, you can see a shot of the audience. There's the school kids in their uniform 60 years ago. And take a look at the guy top left there. He's having a whale of a time. I think I was sitting about there. So you can imagine the influence Lawrence Bragg had on me, and it's one of the reasons why I eventually became a crystallographer. So now, what's this stuff perovskites? What's it all about? What I'm going to try and do is tell you a little bit about the structures of these materials, and then we're going to look at why they're important, and I'm going to look at a couple of the physical properties that they have to show you just how versatile this particular material is. The perovskite, it was discovered in Russia, in the Urals, by Gustav Rose, and he named it after the Russian mineralogist Lev Alexeyevich Perovsky. And that's where it's at. These are the typical pictures of crystals. They're minerals. And chemically, calcium titanate, CaTiO3. And that's where they sat for most of the time, just curious minerals. But when we get into the 1940s, it began to be realized that these materials, based on this formula, are very, very important, very significant. Chemically, they start from this idea, ABX3. Now, A and B are positively charged atoms or ions, like barium and titanium and lead and zirconium and so on. And they're positively charged. X is an anion, negatively charged ion, usually oxygen, but sometimes chlorine, fluorine, iodine, and so on. Most perovskites we know of are oxides. And so here are a few examples. So we have here calcium titanate, barium titanate. This is a very important industrial material. It's used in capacitors, electronic capacitors, for example, many other applications. Lead zirconate. This is potassium copper trifluoride. And then we have sodium bismuth titanate, which is where the A cation is replaced by a mixture of sodium and bismuths, 50-50 of that. And this is a key material today because of its use in a field called piezoelectricity, which I will come to. I've worked for many years on a particular series called PZT, and I hope to come to that later on. This one is a new material, which is a possible competitor for that. My wife, Pamela Thomas, Professor Thomas from Warwick over there, is the world's expert on this particular material. Okay, moving on. So what I've done here is I've drawn out the publications which contain the word perovskite in them over a period of time. When I started, which was 1969 here, there were around 50 to 60 publications a year. That meant I could read pretty well every paper. Easy. But look what's happened. It's enormous change. This jump here, 1987, was the discovery of the high-temperature superconductors, Nobel Prize to Bednorz and Müller. Everybody wanted to have publications on high-temperature superconductors, and they are based on basic arrangement, crystallographic arrangement we have for perovskites. And it carried on and on. Look what happened last year. 22,400 publications last year. That's more than 60 a day. In the course of this lecture, there'll be 2 or 3 publications coming out. How on earth is a scientist today working in perovskites going to be able to keep up with the literature? How are they going to know whether somebody else is working on the same thing as them? This is a really serious problem. What happened last year? 6,500 extra publications. It was a discovery of a new effect in certain classes of perovskites. It's discovered that some of them you can use as solar cells. And now everybody around the world, every scientist in the world wants to get a paper published on solar cells. The world has gone crazy. And it's a subject which is in its infancy. It's going to be very interesting to see where it develops. This was discovered by a colleague of mine, Professor Henry Snaith, in our department. And it's shaken the world, really. So these perovskites, whatever they are, which I'm going to show you a bit more about in a minute, are really, big stuff, this is. Okay, where do we find perovskites? Well, you're standing on it. You see from this little slide here, there's a mineral called Bridgmanite. Percy Bridgman got the Nobel Prize for this. And you see that 38% of the Earth is perovskite, it's a type of perovskite. It's magnesium silicate. Same formula, MgSiO3, ABX3. And 93% of the lower mantle is perovskite. So it's everywhere. It's a very common substance, and yet a lot of people don't know anything about it. Now, I need to, at this point, talk a little bit about something that's important in crystallography so that we can understand what we're looking at. And I illustrate it with a brick wall. You see a lot of bricks, and what you'll notice is the bricks repeat in a pattern. So they're stuck together. This is a type of symmetry that we call translational symmetry. And the same thing happens in crystals. We have atoms and molecules which repeat on and on and on in 3 dimensions, rather like 3-dimensional wallpaper. And that symmetry is translational symmetry. Translational symmetry lies at the heart of our understanding of the solid world. It's the most essential symmetry point in solids. Now, if I wanted to describe this wall, let's assume all the bricks are identical, make life easier. How could I do it? Well, I could write down the positions of all the bricks. And of course, in a crystal, if we're doing this, the bricks are tiny. We have zillions of them in all directions. We would be writing down a lot of paper. We would be covering sheets and sheets of paper with numbers. What we can do instead, and this is what crystallographers do, they say, forget that. Let's just look at one brick, describe that, and then say, let's apply translational symmetry, and we generate the rest of the wall. And we've saved ourselves an awful lot of work. And that leads me to the concept of what we call the unit cell. The unit cell is a part of the crystal, contains atoms and molecules, and if we stack those unit cells together in all directions, we build up a physical crystal. So if I take a crystal of quartz, for example, this is quartz, everybody knows quartz, we have little silicon dioxide units, and we repeat them in a particular pattern, and eventually, if you do it enough times, you build up an actual crystal like that. And we know this because of the work of the Braggs, because developing this X-ray crystallography allows us to determine the positions of the atoms in these crystals. Sodium chloride over here, this is a unit cell of common salt. This repeats over and over and over again in all directions to build up your salt crystal. So I hope that's easy. This is the only real sort of thing I need to teach you about in crystallography for the purposes of this talk. But we will look at some structures as well. So we're going to build up the structure of the basic perovskite for you. And in this diagram, the right-hand diagram is a stereo diagram. And those of you who have got stereo specs, so what I've done is I've drawn a unit cell in the shape of a cube, and I put the A cation in the center of the cube. That's easy. I hope everybody can do that. That's no problem. Now, I'm going to add the B cations, and I'm going to put those on the corners of the cube, the blue things. So we're getting there. Now we've got two lots of positively charged ions. We need some negatively charged ions to balance the whole thing out. So we're going to put some negatively charged anions, oxygens perhaps, and add those. And I put those along the sides, halfway along the sides. And there is my unit cell of the perovskite structure. Very easy. I hope everybody can visualize that. Very simple. Let me extend this a little bit. So let's just put bonds between the blue and the red, between the B cation and the anion. And I've drawn those slightly larger. And then I'm going to add in the oxygens, the anions, in neighboring unit cells. So, for example, let's see if this works here. This anion here belongs in the unit cell not shown to the left. This one behind, this one in front, and so on. And what you can see, I hope, is that if we look at this B cation, there are 6 anions around it. So now what we can do is we can join up the dots. We can join up the red atoms, and we form these octahedra. So we have these solid shapes with 8 faces. We call them an octahedron. What you can see is now, to describe the structure, one of the ways we can do this is say, well, we've got an octahedron here, another one here, but they're joined together by that common atom. In fact, usually when I draw these things, I leave out the anion, and we draw it just like that. So there is your basic structure of the perovskite. What we have is an infinite array of octahedra in 3 dimensions, joined by their corners on and on and on. Very simple, highly symmetric structure. So why is this important? Well, it's important because we can do things to the structure. We can make very, very small changes to it. We can move the atoms about a little bit, tiny amounts, change the basic symmetry, change the structure. And when we do that, we can generate very often remarkable properties, which we can use in an industry, for example. And we're going to see some examples of that. So here we are, all these octahedra joined up to make an infinite framework like that. Now, these are the sort of things we can do. A top diagram, we could take one of the cations here, and we can move it off center. It's exaggerated, but get the idea. We put it in one direction. If you do that, you've put more positive charge in a certain direction, and the crystal has become electrically polar. That means we can do electrical experiments with it. And that's what happens in materials like barium titanate. Structure was solved in 1945 by Helen Magor, and I'll say a few words about Helen in a moment. Even before then, Nari Szabo in Hungary during the war, this is a remarkable piece of work, he was able to produce this complicated structure. You see the octahedra had been tilted to form a rather complicated pattern. That's calcium titanate. That's the original mineral perovskite. That's its structure. The other thing we can do is we can take an octahedron on the bottom line there, and we can stretch it or squash it. We can distort the octahedron. So with these three things, we can create a lot of different structures. And then what we can do, we can change the chemistry of these. We can substitute some of these cations or anions with other atoms, make mixtures of them. So we have a very, very rich field that we can explore and see whether we can make materials which are useful to us. Unit cell distortions, and the unit cell itself gets distorted in the courses by a very small amount, and we often refer to these as pseudo-cubic unit cells, so the cube is slightly distorted. And there are many versions of this materials, thousands of other materials which are based on this idea. Here, just a few. You can see so-called Dion Jacobson, Ruddleston Popper, or Revilius, and the common thing is they have these corner-linked octahedra, but sometimes with gaps in between to make more complicated structures. This is a very complicated area to study. And here are the high-temperature superconductors on the left, lanthanum and copper oxide, the one that got the Nobel Prize. Again, it's not exactly a perovskite, but it has these layers of octahedra which are corner joins, and so it's very closely related. And then the famous IBCO, yttrium barium copper oxide, discovered later. It has octahedra there, those bluish ones, and the very dark blue ones, half octahedra with the copper atom inside. And that's the high-temperature superconductors. We still don't understand how they work. And here's a list of the sort of properties that perovskites show. I won't go through all of them. Dielectricity, piezoelectricity, which I'll talk about, pyroelectricity, semiconductivity, superconductivity, magnetism, high thermopower, catalytic conversion, and photovoltaic. That's its latest discovery as of last year. And we can go on. There's loads and loads of properties, all because we can move those atoms around in tiny amounts. Remarkable. Now, I owe a debt to two very special women. The first one on the left, Kathleen Lonsdale, who was my PhD supervisor. She was a student of W.H. Bragg. So I've always considered W.H. Bragg to be my scientific grandfather. On the right is Helen Magor, who I went to work with in Cambridge. She has a mineral named after her perovskite called calcium stannate, CaSNO3. It's called Magorite. And she was a student of the genius John Desmond Bernal, who in turn was a student of W.H. Bragg. And one of the constant jokes between us, her and I, despite the huge age difference, we shared the same grandfather. It was Kathleen Lonsdale that recommended me to go and work with Helen Magor. And it's she that introduced me to the perovskites, which I spent the last, 45 years working with. So I owe a great debt to these two great scientists. Now, as a scientist, when you develop something, you send it for publication. And what happens then is you expose yourself to the world. And if you've got something wrong, it's your neck that gets chopped. So there's always this bit of sort of nervous tension with a new piece of work. And this is what to do with the subject that Helen Magor asked me to deal with. And this is something that she was working on when I came. Now, I have a couple of models here. She was looking at these octahedra and asking the question, if I take an octahedron from that basic structure and rotate it, tilt the octahedron, what happens to all the others? And she was playing with, this is one of her models that she was playing with. This is another one that she was working with. She never used computers. She used models, and she used her brain. She was the only person I know of who could visualize a crystal structure like this, for example, in her mind. And if you say to her, what does it look like down a certain direction, she'd take out a piece of paper and draw it for you. Today, we have to use computers to do that, but she could do that in her head. A remarkable woman. This, by the way, is a model, what we call a ball and spoke model of a Perovskite structure, more complicated than the basic type. It's actually gadolinium ferrate, but it's the same structure as the calcium titanate, the original Perovskite. And it has tilted octahedra and displaced cations all mixed together. It's a little complicated. So it was Helen that posed for me this problem. How do you explain that what can happen if I take an octahedron and I tilt it? And I'm going to try and show you a little bit about that. So this is a layer of perovskites, of octahedra. So there's one layer, there's one axis coming out towards you, one to the right, one to the bottom. And you can see they're all lined up nicely. So what happens, supposing I take this octahedron here and rotate it about the axis coming towards you, like this. So I've rotated that octahedron clockwise, but it's joined to all these other ones, and so the other ones must go the other way. And what you see, first thing you see is that the repeat distance of the unit cell is not this distance as it was before, it's twice as far, it's doubled, 2a. And also the same in that direction. So that layer, we immediately can see what happens if I just rotate one octahedron about an axis. What about the layer of octahedra above this, which you can't see? Well, there's two things we can do. We take that octahedron there, think of the octahedrons above that. Supposing I rotate it the same way, then it'd be completely hidden. And that I call plus. See, plus. Look at the sign plus. The layers are in phase. And that is one new structural arrangement. And one of these models, which one is it? Let me see. That one is the model that shows that. You can have a look at these later at the end of the lecture. So there is the Perovskite with no tilts, and then with a single tilt about one axis. The other thing we can do is tilt the octahedron in antiphase as you go along the direction towards you. I write a minus sign, and that's the other one. So just putting one tilt into the structure, we generate two structures. So here we are, three structures, no tilts, one tilt, one tilt. And we can carry on. We can say, well, what happens if I now tilt the octahedra in addition about the other two axes? So I can put in two tilts. That's what these white things are. These are two tilts. There's three possibilities. And then what happens if I put the tilt about all three axes? Here they are, the red ones. There are 4 of those. There are 10 possible arrangements. And if you now add into this the possibility that the angles of tilts are different, I worked out that there were 23 possibilities. Later, it was whittled down to 15 by symmetry arguments. So there are actually 15 distinct structures of tilted structures without even displacing the cations. You can now displace the cations, make new structures that way, change the chemistry of it, and you have an enormous variety of fields. But the essence of this, the tilting arrangement, in its heart is very simple. Let me tell you the story. I wrote a paper on this in 1972. I sent it for publication. Back came referee's report. 6 pages, closely typed criticism and comments. I was furious. I was only young, impetuous in those days, not like now. So I went to Helen, furious temper, said, look what this damn referee has done. How dare the referee criticize my work like this? She eventually calmed me down, sat me down, and she read through the referee's report. And so she said, well, look, I'll help you with this. Let's see whether we can satisfy the referee. So she helped me with that. I revised the manuscript, sent it back in. It was a much better paper. Back came 2 pages of closely typed comments. Again, I lost my temper. Went to Helen, and again, she sat me down, calmed me down, and we worked through it, and the paper got even better. And that's the paper that was published, and it's the piece of work that I am probably most famous for, because it established a notation that we can use to describe these tilted structures, and today that's used internationally. It was when Helen retired a few years later that she confided with me that she had been the referee. The editor, by mistake, had sent it to her, and she wrote back to the editor and saying, well, Mike Glazer works for me, but if you trust me, I can be absolutely objective. That tells you a lot about Helen. Now, this thing, for many years, it sort of sat there in the literature as a curiosity, a bit of nice academic research. But in the last few years, understanding this has become very important, because now you can use these different tilt systems. You can do things to perovskites, create these tilt systems, and it has effects on the cations. And by doing that, you change the physical properties. So today, when we look at modern materials, they very often have these different tilt systems, plus chemical substitution, plus displaced cations, to try to understand the properties. So it's become very, very important. I never imagined that. Now, this diagram, I plotted the radius, the ionic radius of the A cation against the B cation. And what you can see, it kind of breaks into two fields. Up here, the A cation is largest. There are no tilts in the structure. It has that structure. It may have some displaced cation, but there are no tilts. And down here, we have tilts. The structure's down here. So bismuth ferrate, for example, here has tilts. Strontium titanate, this one here, has no tilts at room temperature. When you cool it, it produces that structure there. It tilts. So you can think of temperature really as kind of going down here. So this is near the border, and you cool it, it tilts. Calcium titanate here lies just below the border, and it has this tilted structure here, and so on. This is lead zirconate. You can mix it with titanium along here. Lead zirconate is tilted, and as you add titanium to it, it becomes untilted. So you can begin to see patterns here. There's another thing that perovskite people are interested in, I think, called the tolerance factor. This is due to Goldschmidt in 1925. This is the formula. And all it is, it's a stability factor. I've drawn a line, which this is the Goldschmidt line here. And it more or less fits that. The tilts are down here and there's no tilts above there. It's not perfect, but it gives an indication. And what that says to you, forget about quantum mechanics, forget about electronics and so on. Size matters. Geometry rules in this field. And so if you look at this cartoon, what you see is that as we get tilting, the shape in between the octahedra changes, and that allows the cation to move. And this diagram's to left and right, so you can force the cation to form polar structures or antipolar structures as you want. There's a strong link between the octahedra, the tilting of the octahedra, and the movement of the cations into different structures. Clearly, if the cation is very small, and there are even perovskites that have no A cation in it, if the A cation is very small, then you can tilt very easily. But if the A cation is very large, it pushes against the octahedra and stops the tilting. So you can see how the geometry of this is important. Perovskites are used in industry in a variety of different formats. Crystals, single crystals. This is lithium niobate here. And if I can have the overhead a second, let me put that on. Put the lamp on. This is a little crystal here. It's just a small one here. This is lithium niobate, LiNBO3. It's a perovskite. It's used in industry, in the optical communications industries. Very important material. You can grow it in much bigger crystals than this. This is just a small one. I'm grateful to my colleague, Dr. Prabhakaran, who's here for giving me this sample to show you. So this is a man-made crystal. It's grown from the melt by a special technique. Let's go back to the, the Czochralski pulling method, where you melt the material, and then you have a fiber in here with a little seed on it, and you rotate the fiber, and you pull it out gradually, and you get a crystal. This is how silicon's grown. Silicon crystals as big as this can be grown with this technique, the Czochralski technique, very commonly used. So that's single crystals, and this is a newer crystal that's grown in this kind of way. PMNPT it's called. It's lead magnesium niobate mixed with lead titanate. And this was an important discovery made about 15 years ago. You can grow big crystals of this, and this is used in a number of important industrial applications. So you can grow large crystals of that. Usually, it's very difficult to grow crystals that you can use. And so a very common use of perovskites is in the form of ceramics. So this is a micrograph of a typical ceramic. It consists of a random collection of very, very small crystals. So it's a powder. It's a compressed powder, just like a pharmaceutical tablet. And that's a very common use of perovskites in industrial uses. And then more recently, a lot of work is done on thin films on a substrate. So you can deposit a very thin film of the perovskite, maybe just 1 or 2 units cell thick. And with this, you can start to make interesting models, because the interaction between the film and the substrate becomes important, and that interaction between them can cause changes to the structure in the film, and hence the properties. And there's a lot of research over the last 20, 30 years in working on that. Okay, so this is the first of one of the properties I want to talk about. It's called the pyroelectric effect. The formula is given up there on the top. And what it means, this says a change in temperature gives me a change in electrical polarization. In other words, it develops a charge. It senses a change in temperature. Pyroelectric material doesn't sense temperature. It senses changes in temperature. You've seen it many times when you walk past a house and the lights go on. That's using a pyroelectric material. It senses your body heat as you move. If you stand still, the lights go out. As soon as you move, the lights go on. This is the pyroelectric effect. And it was first seen a long time ago. I've got here 400 BC by Theophrastus with tourmaline crystals. And they found when you heat tourmaline crystals, it attracts bits of fluff and dust. It gets charged. One thing about this is that in order for this effect to occur, we must have a polar structure. In the perovskites, that means cations must be displaced altogether in a certain direction, so that one end of the crystal is positively charged and one end of the crystal is negatively charged. And we call it a polar crystal. And we need that if we're going to get the pyroelectric effect. And there's some examples. Lithium tantalate, it's rather like my lithium niobate that I showed you before. Lithium tantalate is commonly used pyroelectric material. And you can grow huge crystals of that. And then we have this PMNPT that I showed you the large crystal of. There's its formula. Here it's a complicated beast. Lead is the A cation. The B cation is magnesium, 2/3 of it, magnesium 1/3, niobium 2/3 with oxygen. And then it's mixed with lead titanate to form what we call a solid solution. It's a complicated beast. And yet, you can grow really nice crystals of that and use these as pyroelectric detectors. So that's an important material. These are used in intruder alarms, motion sensors, infrared sensing, pollution, and so on throughout the world. This is a very important effect. Here you can see some more on this, some of the advantages of the system. Room temperature, it works at room temperature, so you don't need to have to cool these materials, as you often do with thermal sensors. It's very, very sensitive. You can make little devices, as in the photograph on the bottom left. And with this, you can sense people's movements. You can use it in spectrometry, flame and fire sensing, environmental monitoring, energy management, and so on. So there's a lot of wide range of applications for pyroelectrics. Here's some examples again. This on the right there is a crystal lithium tantalate, very, very good pyroelectric material. In the top is not a perovskite, not even a crystal. It's a piece of plastic, PVDF, which is also pyroelectric, so you can get plastics. And then these two on the bottom left is a slice of ceramic with this rather complicated formula. So here we have lead as a A cation, and the B cation is 0.58 zirconium, 0.2 iron, 0.2 niobium, and 0.02 titanium, and then oxygen. So real materials, as used in industrial applications, are really rather complicated compared with our starting point here. So trying to understand these structures and how they work in these environments is really quite tricky. I owe this slide to my colleague, Professor Roger Watmore, who's somewhere in the audience. Where's Roger? He's there, he's waving. Roger is probably the world's expert on pyroelectrics. He was my first research student in Cambridge. He's now professor at Imperial College. And he lent me this slide. So this is to show you how one of the ways in which you can use ceramic perovskites in an application. So what we have here on the left, we have an array of little tiny elements of perovskite. The perovskite we're using is this fellow here, who I already mentioned to you, this rather complicated thing here. It's got zirconium in it, iron, niobium, titanium. It also has a mystery ingredient, which I won't tell you about. So we have some object here which is emitting infrared radiation, a person, something warm, and we can focus the thermal signal onto this array, and at the back of the array we can make electrical connections and attach that to a bit of electronics and plot a picture on the screen as each of these elements responds to the signal there. However, the problem is it won't see anything because this is a static image. So one of the ways in which you can get this to work, if nobody is moving here, if this is just a static person, it's actually stationary, you can put a chopper in here, chop it around, and that changes the thermal signal and creates the image on the array. So it's a simple idea. Originally, these things were developed for the military, and had huge arrays of these things, and it was very, very expensive. But now they're made very cheaply, and I'm going to show you a bit more about that in a moment. Now, this is something that Roger and his colleagues did some years back. It won an award. And there's a fire in a room, you see, and the room is filling with smoke. And somebody's in there. Now we switch on the device, and we can begin to see what's going on in this room. Here come the firemen into the room. You can make out that they're there, and they're now going to find the people that are trapped in this room. And they go around, there's somebody there. You can see some person sitting in a chair, and they just work a bit more. There's something. Is that a baby there or something? Yeah. Yes, it looks like they found a baby in there. So this shows you how you can use this type of application when lives are threatened in a fire, for example. So it's a very, very useful way of using particularly perovskites. Now, there's a company up in Northampton called Emeritus who manufacture a device, which you can see on the top left here. It looks rather like a smoke detector. But what it does, it senses people's motion using an array. And what they use is a fairly crude array. Here's the array. And when people walk underneath it, they create a signal as they move. Very poor resolution. But they don't need high resolution for this, because you can computer processes and decide whether these are people. Sometimes you can decide whether it's a cat or a dog or something, or whether it's a fire that's starting somewhere. And so you can sense people. And the great thing about this is, unlike CCD cameras, which take an image of you, this preserves your personal privacy. So you can use this without offending anybody. And Emeritus manufactures this system. It's relatively cheap, and it's used all over the world in different applications. For example, the sensing in supermarkets, the sensing people coming into the checkouts in order to manage the queues. It's used in security environments, at airports and so on, people counting people going through doorways and coming out through doorways. And we have a couple of these installed here, just one there and one there, just above the door. You've all been counted in. And that's useful because when you go, we're going to count you out. Make sure you'll leave. I'd like to introduce, actually, at this point, Dr. Tony Holden from Iris's company. Where is he? Oh, he's over there. And Tony's going to show you what we found when you came into the lecture room. Hopefully, we've recorded the image. So if you'd like to do that, Tony. So you press the appropriate button. Hopefully, we'll see it somewhere. What's that? Okay, so the two doors, and you can see on the left of each one is the CCD image, but on the right-hand side, you can see the people coming in and out, or individuals as they come in and see them wandering around, thinking, am I going to come into this lecture room or not? Perhaps I should escape. And you can see the numbers at the top there. It's counting people coming through these two doors. And this is a very useful thing because at the end of the lecture, we don't want anybody trapped inside here. We want to know that you've all gone. And it's very nice because you see you can't tell on those pyroelectric images who those people are. We've preserved your personal security. Simple, very simple idea. Brilliant, though, in its application. And this company, Emeritus, it's the only company in the world that produces this kind of technology, and it's a British technology. Very important. So I think a round of applause for Tony, please. Here's Euston Station. This is counting people going through a doorway at Euston Station. You can see on the left the normal image, on the right the pyroelectric image. You see crowds of people going one way, people going the other way, and it's counting them through the entrance at Euston. You didn't know, did you? Every time you go through Euston, you're being observed like this, but you are. Okay, so that's one of the effects that perovskites are particularly good at. The next one is what we call the piezoelectric effect. Now, what that is a phenomenon found in 1880 by two French physicists, Jacques and Pierre Curie. Pierre Curie was the husband of Marie Curie. He was a very bright guy, and he discovered that in certain crystals, like quartz, here is quartz, our old friend quartz, if you cut slices of it, it has an effect which was termed piezoelectricity, and what it is, it converts mechanical to electrical energy. You've all seen firelighters like this. You get a spark when you press this button. I hope most of you have seen it. You light your gas fires with this and so on. No batteries in there. Inside there's a couple of pellets of a Perovskite ceramic called PZT. And when you do that, a little hammer hits the PZT, and the mechanical energy, due to my movement of my thumb, is converted into electrical energy. You get a spark. And that will last essentially forever. And that's piezoelectricity. So the formula, sigma on the right, is a stress that we apply to the material. And on the left, we again get a polarization, an electric charge. So it's like the pyroelectric effect, except the pyroelectric effect is temperature change. This is, if you squeeze the material, if you put pressure on it, you generate a charge. So that's the piezoelectric effect. And you can see here, whoops, go back. You can see here, we apply stress to it, and we can read on a meter the change in the charge and use that electrically. Now, Gabriel Lippmann showed actually you can do this in reverse. You can apply an electric field to the material, and you can generate a strain, which in other words, change the shape of the material. It's called the converse effect. You can run piezoelectric in these two directions, either way, as you wish. Either convert electrical energy into mechanical energy, or mechanical energy into electrical energy. So this is beginning to look interesting. Now, so where do we use it? Here's a few of the applications that piezoelectrics are applied to. In the automotive industry, airbag sensors, airflow sensors, audible alarms, fuel atomizers, buzzers, and so on. Buzzers where you apply an oscillating electric field, the material changes shape and it goes bzzz. Buzzers, just simple buzzers. Computers, disk drives, inkjet printers. In consumer market. Cigarette lighters, nobody uses those today. Depth finders, fish finders, humidifiers, jewelry cleaners, musical instruments, speakers, telephones. What else have we got here? In medical, disposable patient monitors, fetal heart monitors, ultrasonic imaging. In the military, depth sounders, like sonar, hydrophones, all those sorts of systems uses this piezoelectric effect. I've even seen this one. This is handle of a tennis racket. It has inside it PZT fibers, Perovskite fibers in here. And the idea of this is when the ball hits the string's going to start to oscillate. Well, that mechanical signal goes to these fibers, creates an electrical signal, that gets fed back in opposite, and the fibers change shape, and it damps out the oscillation of the strings. A rather clever application. The market for ceramic piezoelectrics, look at it. It's billions. Predicted for this year in different applications, as much as $14 billion. This is very big business, worldwide business, piezoelectrics, particularly ceramic piezoelectrics. Most of them are this material PZT that I mentioned, which is lead zirconate titanium. That's the material I've spent the last 45 years of my life working on. I think as of the last couple of weeks, I finally understand how it works. It's very, very complex. I will not bore you with all the details. And this is a thing you can do. You can make motors. So what's happening? This is done by a nice company in Denmark, PCB Motors. And so what they do is they have a ring of piezoelectric elements, PZT elements altogether. In fact, I can show you that if we put this here. That we can have this visualizer on a second. So this is it here. It's a tiny little thing. And all around here are little piezoelectric elements. And you send an electrical signal that goes up and down all the way around, and the little piezoelectric elements change shape. And so if I go back to the PowerPoint, so it's rather like a Mexican wave. You see it goes up and down like that, and if you put a disc on there, it starts to rotate. So here's an example where they put a coffee cup on it, and then it rotates. This is my own one here. This is one of my models of Perovskites, which I've put on there. You can see rotating. And this is a high-speed one, which Professor Roger Watmore has done. So you can make interesting motors. No magnets, not like the original motors. Years ago, I wanted to get a motor without a hole in the center for doing optical work. I couldn't find one except under £10,000. They were very expensive to do. This, for 300 or 400 euros, does the trick. Very, very precisely. You control it just on a computer. And it's a brilliant idea. That's using PZT perovskite. Who knows what this is? Sonar here. Somebody has a sonar. Okay. Well, there's a very interesting history here. Originally, it was called ASDIC, A-S-D-I-C. Nobody knows what ASDIC stands for. There are a couple of ideas. An anti-submarine detection investigation committee was proposed. Nobody's ever found a mention of that committee in government documents. Somebody else said anti-submarine division or anti-submarine division X. Who knew? Nobody knows. So the idea is a ship has a piezoelectric crystals, creates an ultrasonic wave by putting an oscillating electric field on. The material vibrates. Ultrasonic wave goes out, bounces off your enemy submarine, comes back, and that pressure wave now interacts with your original piezoelectric. Using the direct piezoelectric effect, creates an electrical signal. So now you can time the distance between the wave going out and the wave coming back. And if you work at high frequency, you can focus this very narrowly in directions and determine where that submarine is and how far it is. This is called ASDIC. There's an interesting story here. Back in the First World War, W.H. Bragg was employed by the Navy to work on anti-submarine detection. And they set up a unit there, but they ran into trouble with the Navy officials who didn't trust the civilians. And so contact between the two was rather fraught. W.H. Bragg worked on hydrophones, and it was kind of mixed success. Now, during this time, the French physicist Paul Langevin suggested using piezoelectrics for this kind of purpose. And so work began, highly secret work, at the end of the First World War, into the interwar years and into the Second World War, on what was called ASDIC. It was so secret, people were not allowed to mention the material they were using. The material they were using was quartz. This is an artificial quartz crystal. This is a natural quartz crystal. This was a strategic material, not a perovskite. This was the material that we're using all the time. It was so secret, they were not allowed to mention quartz. They had to call it asdivite. In the Second World War, more research was done on new materials for this application. And W.L. Bragg was a consultant in Fairley in Scotland with the Navy to find new materials which you could use to replace quartz, which is not the world's best piezoelectric. And they were playing with different materials. One of them was ammonium dihydrogen phosphate, not a perovskite, ADP. But you can grow big crystals of it, and here is a crystal of it. Big. This, I believe, is actually Lawrence Bragg's crystal from 1944. Then the Americans were working on another type of material called Rochelle salt. Shortly after that, around 1944, thereabouts, barium titanate, BATiO3, the first perovskite, was used as the transducer used in ultrasonics for detecting submarines. And the application of piezoelectrics is really what essentially put an end to the U-boat fleet in the Second World War. So it's a very important development. Barium titanate was the structure that Helen McGaw solved in 1945. And then we have PMNPT, a more recent crystal, and a couple of great examples of it used in medical imaging. So we have the famous dancing baby in the top and heart valve in the bottom. High-resolution images where you do exactly, it's a sonar. It's exactly the same thing as ASDIC and sonar done for medical purposes. And I was going to finish up just by showing you a little bit about this famous PZT. This is what we call a phase diagram. The vertical axis is temperature, and on the bottom we have composition. So on the left is lead zirconate, PbZrO3, on the right is lead titanate, PbTiO3, and then we change the zirconium for titanium along the horizontal line. And you'll notice different fields. In high temperature, up there, no tilts, no displacements. It's this structure here. When we cool it, at this region, we get the cations, the lead atoms, displace in the vertical direction, making a polar structure. Then on the left, we have, again, two polar structures. So the cations are displaced, but along a different direction, along the diagonal of the cube. This one here, in addition, has tilted octahedra. It's one of these red ones. So it's really quite complex. But the vertical, nearly vertical line is called the morphotropic phase boundary, or MPB. And this is where you make your materials with the highest piezoelectric coefficient. It rises to a maximum at this point. And that's the thing that I've studied most of my last 40 years or so, trying to understand how that works. Why is it the maximum there? Because if we can understand it, we can start to think about making new materials. And a few years ago, a colleague of mine, Beatrice Nahida, discovered actually in here, there's an additional phase called a monoclinic phase. It's a low symmetry phase. And this caused a lot of excitement in the scientific world. It became the hot topic of its time. Hundreds of papers suddenly started appearing, investigating this monoclinic phase to try to show how that caused this rise of piezoelectricity. One of the problems was, while there's a boundary here, you could never find a boundary on that line there. And that was one of the mysteries, and it's one of the things that we worked on to try to understand. So that's PZT, one of the most important piezoelectric ceramics in the world. And there are two things that contribute to piezoelectricity. One is called the intrinsic effect. So this is where you apply a stress or electric field and you move the atoms in the unit cell. You see the atoms go up and down, and by doing that you change the polarization. So this is an atomic effect. This happens at the atomic level. It's called the intrinsic effect. And that's one of the ways you can generate piezoelectricity. And in PZT, what happens is on the that left-hand side of that phase diagram in particular, the lead atom is displaced in a certain direction, within a plane, and it can rotate in that plane as you apply the stress. So you apply that lead vector changes the polarization, creates a piezoelectric effect. And there's been a lot of argument as to whether this so-called polarization rotation effect really happens or not. We believe it does happen. We have evidence for that. And that's part of some papers we've been publishing recently. The other way you can get piezoelectricity is known as the extrinsic effect. This is very complicated, not properly understood. But one of the models for doing this is where you have a crystal which has two regions in it. So this is not unit cells. Each of these colored regions here contains zillions of unit cells. This is on a large scale. And you see that this region, the crystal, is different from that region, the crystal, the polarization points in different directions. And if you can make that domain wall move by applying a stress, you change the relative balance of the polarization, you induce a polarization, and there's your piezoelectric effect. Now, that's not the whole argument. There are other people who have other arguments which say, well, you don't need to move the domain walls, just have a lot of domain walls will do this. And PZT, in the center of that phase diagram, when you look at it under the electron microscope, has lots and lots and lots of tiny domains in it. So that's obviously tied up with it. And barium titanate there, you can see different domains in barium titanate. We can see those in the optical microscope. So there's the MPB in PZT, and here this is the measurement of the piezoelectric effect. You can see that it rises to a maximum around the center of the phase diagram, falls away very rapidly on this side, but falls away slowly on that. And that's something we've been working on. We now know, as of this week, actually, why that happens, why that's a long tail there and that falls off. And what it is this is a mixture of intrinsic and extrinsic effects, whereas this part is almost purely extrinsic. These two different mechanisms give rise to that asymmetry. So now we're beginning to really understand the origin of this. And I'm going to just show you very quickly now, before I finish, a cartoon. This is how we envisage what you might see, if you could see this, at the atomic level in a crystal grain of PZT. So we have unit cells, these little hexagons in this case. Hexagons because if you take a cube, look down the body diagonal, it looks hexagonal. And what we find is that in this crystal, it's a disordered crystal, we have regions, red, these I've colored them green, blue, red, where all the polarization vectors are in the same direction. So those regions are ordered, they have translational symmetry that we started with. But in addition, we have regions where it's all randomized. So this is a horrible mixture. PZT is an utter dog's biscuit. It really is a complete mess. So when I started, crystals like this were periodic. They continued in all directions. Now, when I look at crystals, they're all full of mess. And it's this mess that's important in understanding these properties. This lies at the heart of explaining that effect, that piezoelectric effect that we see in PZT. I believe now we fully understand, pretty well fully understand, how that PZT works. And this is the latest. These are what we call hybrid perovskites. So the A cation here is an organic group. I think they got the formula not quite right there. Lead is now the B cation, sits inside the octahedra. The octahedra have iodine instead of oxygen. And at high temperature, we have the octahedra all untilted. The organic thing inside, it exists in different orientations. So when you average it out, you get this sort of mess of organic fragments. We don't know for sure if these are rotating dynamically or whether it's just as you go from one unit cell to the next, they're just in different orientations. You call it, the evidence is you start to get tilting. This has got one tilt, so it's like that green one there. But in addition, you see that it has an effect on the organic fragment inside. It's less disordered than it is there. And we lower the temperature still further, and we have three tilts, like one of these red ones here. And again, we simplify the organic fragment. That's a structure determination. There are other people that have been doing structure determination with slightly different results. It's still a matter of controversy. We don't understand the structure. We don't understand why it gives rise to this photovoltaic effect, which everybody is excited about. You can see at the top, we've even got a conference coming up in Oxford in September, a third one now, to try to discuss this topic. People will come from all over the world for that. So this is a very exciting area. Nobody knows really where this is going to end, but the number of publications is daunting. And this is the way you make it. You make a layer of perovskite, you put it on some sort of substrate, tin oxide or silicon, so you make these sandwiches and you start to make devices that you can then get this photovoltaic, this solar cell effect. And you can make this very, very cheaply. But the problem is how to keep it stable. And my last slide. Thank you very much.
Can you predict computationally what a given mixture of atoms in a perovskite, what properties it would have?